Let's look at section 5.1, Riemann sums. What we're trying to do is approximate the area between the graph of a function, the x-axis, and the vertical lines x equal a and x equal b. So I have the graph here of y equal x squared, that parabola drawn, on the interval from 0 to 2. In other words, I'm considering this graph between the vertical line x equals 0, which is the y-axis, and the vertical line x equal 2. And I want to know approximately what is the area on this interval from 0 to 2. What is the area underneath the graph of this parabola and above the x-axis? In other words, what's the area A of this region? What's the area A of that region? So we're going to approximate this area using some rectangles. And we've got to know how high the rectangles are to be. So the way we tell you that is we either tell you to use right-hand endpoints to get the heights of the rectangles, or left-hand endpoints or midpoints. So you'll be told to compute a Riemann sum to approximate an area, and you'll be told how many rectangles to use in your sum, and whether to use right-hand, left-hand endpoints or midpoints. Okay, sometimes what we're computing here is called R4. Your book will call this R4. WebAssign calls this R4 because you're using 4 rectangles and you're using right-hand endpoints. Now, the first step is I have to subdivide the interval. So I'm going to go over here to illustrate. I've got to subdivide the interval between 0 and 2 into 4 equal subdivisions. So what are these tick marks going to be? Aren't they going to have to be 1/2, 1, 3/2, 2? In other words, 0 halves, 1/2, 2 halves is 1, 3 halves, 4 halves is 2. This is called a delta x. Each one of these little widths is called a delta x. The distance between successive tick marks here is called delta x. That's called the width of a subinterval. I have 4 subintervals. I've divided my longer interval 0 to 2 into 4 subintervals. Delta x, the width of each subinterval, is just 2 minus 0, the width of the whole interval, divided into 4 equal parts. So I get a half. So again, 1/2, 2 halves, 3 halves, 4 halves. Okay? In general, delta x, the width of a subinterval, is going to be b minus a over n, where AB is this interval over which you're trying to find the area. You'll always be given the coordinates of your vertical lines x equal a, x equal b. N's the number of subintervals. You'll be told that. So you're always given a, b, and n so you can figure delta x. Okay? Now, what I want to do is I want to partition 0, 2 on the x-axis in my graph. So I go from 0 to 1/2 to 3/2 to 2. I have partitioned the interval 0 to 2 into 4 equal parts. And now I just draw a vertical line through each one of these tick marks until I hit the graph. I'm going to draw a rectangle. In other words, I'm going to draw the top of a rectangle over each one of these subintervals. Okay? It tells me to use right-hand endpoints. So the first subinterval is 0 to 1/2. What's the right-hand endpoint of that first subinterval? It's 1/2. So I'm going to let f of 1/2, or the height of the graph over 1/2, be the height of my first rectangle. What's the second subinterval? It's 1/2 to 1. Here's my second subinterval, 1/2 to 1. What's the right-hand endpoint of that subinterval? It's 1. So I'm going to let f of 1, or the height of the graph over 1, be the height of my second rectangle. Similarly, the third subinterval is 1 to 3/2. The right-hand endpoint's 3/2. I'm going to let f of 3/2 be the height of my third rectangle. And the last subinterval, 3/2 to 2, the right-hand endpoint is 2. I'm going to let f of 2, or 4, be the height of that rectangle. So my Riemann sum is the area of these 4 rectangles. Okay, R4, the area of these 4 rectangles, using which we got the height for using the right-hand endpoint, is just the height of the first rectangle. So that would be f of 1/2. The width of this first rectangle is also 1/2. Remember, this delta x was 1/2. In other words, this is 1/2. That distance is 1/2. This distance is 1/2. This distance is 1/2. That's delta x. Width of a subinterval. Okay, f of 1/2 is the height of the first rectangle. 1/2 is the width. So f of 1/2 times 1/2 is the area of this first rectangle. What's the area of the second rectangle? Well, it is f of 1. That's the height. F of 1 is the height. Right? We're using right-hand endpoints. The width is still 1/2. This distance between 1/2 and 1 is 1/2. So f of 1 times 1/2 is the area of this second rectangle. The area of the third rectangle would be f of 3/2. 3/2 is the right-hand endpoint of this third subinterval, from 1 to 3/2. But the width of that third rectangle is 1/2. So f of 3/2 times 1/2 is the area of this third rectangle. And the area of the fourth rectangle is f of 2. because 2 is the right-hand endpoint of this last subinterval, times 1/2. This is called a Riemann sum, and we got it using 4 rectangles and right-hand endpoints. So what's f of 1/2? Well, in this problem, f of anything is what? F of x is x squared, right? That's the function I've graphed. It's this parabola. So f of 1/2 is 1/2 squared. F of 1 is 1 squared. F of 3 is 3/2 squared. And f of 2 is 2 squared. Now, can't I just factor out a half? I can factor out a half here. And what I'm left with is 1/2 squared plus 1 squared plus 3/2 squared plus 2 squared. That's 1/2 times 1/4 plus 1 plus 9/4 plus 4. So that's 1/2 times 1 plus 4 is 5. 1/4 and 9/4 is 10/4, which is 5/2. Five halves is 2.5, so 5 plus 2.5 is 7.5. So that's 15/2 times 1/2 is 15/4. Notice that's just a little bit under 4 square units, right? This is the value of R4. In other words, the area underneath this curve using 4 subintervals and right-hand endpoints to get the heights of those subintervals. Now, realize our area, the exact area under the curve, is approximately 15/4. But notice that these rectangles give us an overestimate. We're way over, right? We're way over. So I'm going to say, but this approximation is too big. We can see a lot of these rectangles being outside the curve. Now, I'm going to ask that you look at an animation shortly. And if you look in the book, in section 5.1, on page... You can tell I'm looking for the page here. On page 367, no, on page 369 in section 5.1, you will see how if you use more rectangles, you're going to get better and better approximations.